The Hong Kong Polytechnic University, PolyU, leverages its world-class academic and research excellence to develop innovative solutions for a more sustainable tomorrow. In July 2022, the PolyU Academy for Interdisciplinary Research PAIR was established as the university's central research platform, dedicated to providing world-leading, interdisciplinary solutions to significant societal challenges. PAIR is composed of multiple constituent research institutes and research centers. Each research unit focuses on a particular research area and is joined by researchers from various PolyU faculties, schools, and departments. These research areas broadly fall under three main themes, including advanced technologies and manufacturing, good health and well-being, and smart and sustainable cities. PAIR researchers develop new materials, systems, technologies, and techniques that support industrial modernization, upgrading, and transformation. Look into the factors and mechanisms influencing human health and wellness and develop evidence-based solutions. And generate smart technology-based solutions for making urban operations and services more efficient, connected, and eco-friendly. We particularly value impactful collaborative activities in research and scholarship. PAIR researchers pursue research collaboration at different levels. In addition to interdisciplinary collaborations within and between research units, PAIR and its units establish partnerships with industries, governmental bodies, universities, and other external stakeholders. With internal and external collaborations, we have successfully translated PAIR-led innovations into commercializable solutions and practical applications, and established joint laboratories and research entities with external organizations, driving scientific breakthroughs, innovation, and technology development, and socioeconomic prosperity. PAIR's research excellence and research impact have been widely recognized at local, regional, and international levels. Our research outcomes have been published in leading journals, including Nature and Science. Innovations led by PAIR researchers have won prizes at various competitions and events, including the International Exhibition of Inventions Geneva. Many PAIR researchers have been named among the world's top 2% most cited scientists in their own areas of specialty. Individual researchers have been selected to the National Academies of Science or Engineering and as fellows of professional associations, and have been bestowed with local, national, and international awards and honors. Harnessing the strengths of PolyU's research and world-class scholars, PAIR will continue our unwavering efforts in research and scholarship, knowledge transfer, and collaboration to develop impactful solutions that benefit Hong Kong, the nation, and the world.
Good afternoon, ladies and gentlemen, colleagues. Welcome to this PAIR Distinguished Lectures series. And before we begin, I would like to invite Professor Wan Zhongkai, the Associate Vice President for Research, to introduce our distinguished speaker today. Professor Wan, please.
Ladies and gentlemen, it's my great pleasure to welcome Professor Julia YEOMANS from University of Oxford to deliver distinguished lecture at PolyU. Let me briefly introduce Professor Julia YEOMANS. She received both bachelor and a PhD from University of Oxford, and then did a postdoc in Cornell University, then returned back to UK to start her career. I met Professor Julia YEOMANS in 2011. I think at the time, usually AMIs was held in early December. At that time, I vividly remember Professor YEOMANS gave a very interesting talk about LB simulation. And then when I returned back to Hong Kong, I encountered some trouble, not trouble, some difficulty in my research. One night, I wrote email to Professor YEOMANS. Immediately, she replied my email. She mentioned, "Oh, your experiment result very cute about the pancake bouncing." Luckily, the paper was published in Nature Physics in 2014. That is my first Nature level work. Today, I think the paper already been cited more than 1,000 times. For that, I really appreciate the effort and contribution and the guidance by Professor Julia YEOMANS. I think what impressed me the most is Professor YEOMANS. She is not only devoted in her research, but she is not afraid of change research direction. Later on, she moved to a new area, which is quite challenging for me, active matter. I think after that, she published quite a lot of paper in high-profile journals, for example, Nature, Nature Physics, and I think Professor YEOMANS also have a collaboration with Professor Yiling, right? I think Professor Yiling, published quite also a lot of high-profile paper in Nature about bacteria. When we contact Professor YEOMANS to give a biography, she gave us a very thin, biography without any awards. Professor Chen, give me a new version here show the award. It's very amazing. Professor YEOMANS was elected a fellow of the Royal Society (FIS) in 2013. But what is more remarkable is over the past 2 years, Professor YEOMANS received a number of awards. Let me mention it. In 2021, she received the Sam Edward Medal and Prize from IOP, Institute of Physics. In 2024, she was awarded Liquid Matter Prize from the Europe Physical Society and also appointed Officer of the Order of British Empire in 2024 for her contribution to the service to physics community. And also 2024, she was awarded the Dirac Medal and Prize. This is very high-level award. During the launch, Professor YEOMANS told me she is the first woman to receive this very distinguished award in history. I think other award already been there more than 50 years. Okay, and also I think she will continue to receive award. Okay, without further ado, ladies and gentlemen, please join me in welcoming Professor Julia YEOMANS to deliver talk.
Hello, everybody. Thank you very much for coming. And thank you for the kind introduction and the kind invitation. I've really enjoyed exploring Hong Kong. It's an amazing island that you have the possibility of all these beautiful buildings, but then the beautiful sea and mountains all around them. I'm going to talk about active matter. And what I mean by active matter is, if we can get this to work. Oh, okay. What we mean by active matter is materials which take energy from their surroundings and use it to do work. So they're always taking in energy and they're always using it to do things, they're engines. And because of this, they always have to be out of equilibrium. They're out of equilibrium. And it's because they're out of equilibrium that their properties are really strange. They can form interesting patterns. So let me start by introducing you to some active particles. And let's start at the tiniest length scale and ask yourself the question, how do cells work? Our bodies are made up of cells, and somehow the cells have to move proteins and enzymes to the right places. How do things move around in a cell so they can do the jobs they're meant to do? And these things are tiny. They're nanometers. And we know that at those sorts of length scales, there are lots of fluctuations, and cells are very crowded. So if something tried to swim from one place to another, it would be in a complete mess because it would be hit by everything around it, and it would never be able to get there. So the cell has to design a way of moving things around. And this is how it works. It lays down things which are like railway tracks, microtubules, and it can lay them down and then dissolve them again. And then these little things here, these feet moving along, are motor proteins. Press the right button. Yep. This little thing here is a motor protein moving along the tracks. And then the proteins and what it wants to move around are put into this vacuole above it. Of course, this is a computer animation of what's going on at the moment inside all your little cells. But let's have a look at a real picture just to prove that it's really true. These things here are those little feet, and they're moving along. This is light microscopy. And I'll show you another movie because I looked up the latest sort of version of how these things move. Again, although it's a computer animation, it's absolutely based on experiments. And here it is moving along the microtubule, a tiny little motor moving along the microtubule. And there's a big problem here, an engineering problem, which is that how does the cell do the control theory which makes these things work? How does it know where to lay down the microtubules? How does it know where the motors should attach? And how does it know what to put in the vacuoles? We don't know. Nobody knows. There's a big question there for you young students to start thinking about. But these systems are used for one of the materials we use for experiments in active matter physics. This is one of the famous systems, a mixture of microtubules, the long, thin polymers, and these tiny motor proteins. What happens is that people have taken the long, thin polymers, the microtubules, out of cells and then put them in a mixture with lots of different motor proteins, and in particular with two-headed motor proteins that bridge between the two microtubules. These things move in a certain direction up the polymers. If two neighboring polymers have microtubules moving in the same direction, they just move like this and nothing happens. But if the microtubules are moving in opposite directions, the microtubules will move like this and they will get mixed up. So what happens is, let's wait for it, is something like this. The sort of white stringy things you can see are the long, thin microtubules, and they're being pushed around by the motors, and you end up with this turbulent-like state. Bit weird, right? We're tiny here. These things are tiny, and we're getting turbulence. We're getting low Reynolds number turbulence. More of that later on. But now let's think of another system, another sort of active particle. Bacteria are active particles. These are E. coli bacteria, and these can swim. They're about a micron or 10 microns in length. These things can swim. And here is a motor which turns their tails, so which propels them forwards. These things are like a little propeller. These are rotary motors. They sit across the boundary of the cell, and they're driven by a flux of proteins moving across the cell boundary. Here's the cell boundary, and this again is an animation showing how these things move. Within the corner, a proper picture just to show that it's real. Each of the different colors is a different sort of protein. This thing's about 40 nanometers across. It's pretty amazing that within a cell, you can construct something like that. You can get these proteins and you can put them together in the right order to give something as complicated as a rotary motor. And it's pretty tough out there in the cell. Things are going to come along and break this. They're going to knock proteins off. So the motor has to repair itself as well. This is a soft motor. It would be great to be able to build something like that. And even in a place like this, where I know you're all wonderful at building things, I don't think it's possible to do it yet. We'd really like to make motors like these tiny, soft motors. If I take the bacteria and put lots of them together, this is what happens. Again, lots of active particles together. You get this chaos, this low Reynolds number chaos, this active turbulence. Epithelial cells do it too. These are squishy cells, the ones that basically are part of your skin and your body. If you take these and you put them in a layer on a Petri dish, again, you get this turbulence, this active turbulence. Weird at low Reynolds number. Turbulence is meant to be a high Reynolds number phenomenon. Let's just look, before I start on the main bit of the talk, now at some active particles which are a little bit bigger. So these are active, they're living systems. Living systems are active. We're always out of equilibrium. Even when you're asleep, you're using energy to do things like breathe. If you come to equilibrium, it's really bad news. Same with little cells. This is a dolphin. I thought it was a shark for ages, but then someone pointed out that if it was a shark, those people there would not be happy. Okay, so it's obviously trying to get its lunch and it's not doing it very well. Somehow the shoal of little fish, the shoal of active particles, is managing to move out of the way. This is a bit different. The physics is going to be a bit different because we're now at higher Reynolds number, but then you can see the sort of patterns that we get there. And just as a last example, with people too, one has lots and lots of people. Sorry about the sound. I had it switched off on my computer, so I didn't know, but it's unimportant. Okay, again, when you put lots of people in one place, you get patterns. They start moving in patterns. And people are using the ideas of active matter to try and understand how to control crowds better, because if things go wrong when you've got that many people, pretty disastrous. So why do I care about active matter? Why is it interesting? Well, first of all, active matter is really the same as biology. It was Schrödinger that first said that. He said that living matter evades the decay to equilibrium. And he was dead right. And it's taken us 50 years to work out, the rest of us to catch on with that. Physicists are interested in active matter physics, and it turns out to be essentially the same thing as biological physics. We're learning about biology. Those tiny engines are very efficient. It'd be great to be able to make them. We'd like to understand how this active matter, which is taking energy and using it to do things, it's an engine. We'd like to understand how it works so we can build robots, particularly soft robots. And I am a theoretical physicist, so what I care about is that this is a beautiful example of statistical physics out of equilibrium. How do lots of particles behave when you put them together out of equilibrium? And this is what I'm going to talk about mostly in this talk. These examples of dense active matter. 3 different examples. I've shown you microtubules driven by motor proteins. I've shown you bacteria. I've shown you these epithelial squishy cells, and they all do this chaotic behavior. It's called active turbulence. And it's described by almost the same theory in those different systems. That's great, because if you're a theoretical physicist, you can't remember anything. So if you can just remember one thing, it all works much better. I'm going to try and explain to you how active pneumatic theory can explain what's going on in these different systems. So first of all, I'll talk about active pneumatics and active turbulence and the sort of theory behind it. And then I'll talk about these examples at the bottom. And I'm going from the first bit is fairly well known in the physics community. The examples at the bottom are our research, some of which is not yet published. So, pneumatics. Pneumatics, what they are is, I'm talking about pneumatic ordering. You probably know about pneumatic liquid crystals. Pneumatic liquid crystals are long, thin molecules, and they have a direction, but no arrow on them. So up and down are the same. And if you put a lot of them together, they tend to order in this pneumatic state, where they all want to point in the same direction. So they have long-range orientational order, but no long-range positional order. They're not on a lattice. These are the liquids you get in your laptop screens. The ordering is described by a Q-tensor. The Q-tensor is the order parameter. In 2 dimensions, it's a 2 by 2 tensor, and its largest eigenvector tells me the direction these things are pointing in, and its largest eigenvalue tells me how lined up they are. If this ordering goes wrong, if you have a small fluctuation, that's fine. These things behave elastically, and very quickly it just relaxes back and everything's okay. But you can have much more important distortions. They're called topological defects, where the ordering gets completely screwed up. So here are some pictures of the most common defects, the most common topological defects in 2 dimensions. And we are going to be in 2 dimensions here most of the time. That one at the top, which looks like a comet, these are the pneumatic colloids or molecules or swimmers forming this shape. That's called a +1/2 defect. This one down here, which has this 3-fold symmetry, is called a -1/2 defect. And the reason that they're called topological defects is that they behave like knots. You can't get rid of them. They muck up the ordering all the way out to infinity. And you can't actually undo one of them without changing things all the way to infinity. So they're behaving like a knot on a circular cable. The only way they can be destroyed is by the +1/2 and the -1/2 moving towards each other and annihilating like charges. Now, I think, yes, this is my math slide, but you know about this because I'm sure you're all familiar with the Navier-Stokes equation. That's the equation that we'd write down to describe how a fluid moves. And this is essentially the same thing as the Navier-Stokes equations, but for this rather more complicated liquid crystal, one which is a structured fluid. Don't worry about the details, they're not important, but I just wanted to show you that when I'm showing you simulations, these are the equations you solve. And I want to ask, how do they change if something becomes active? So these are the equations which describe how liquid crystals move. First, you need an equation for the order parameter. It moves with the flow, and because I've got molecules which are this shape, any sort of flow gradients, any sort of shear flow or rotational flow will turn it or move it. And then you have a term which tells you that if I turn off the flow, this relaxes back to its nice pneumatic state. And then you have an equation for the velocity, and at the moment that actually looks just like the Navier-Stokes equations. There's some extra bits hidden in this stress tensor, but we don't have to worry about that. And we understand these equations. We understand them very well. We understand how they describe liquid crystals. So how do I have to change them if I've now got these active systems? What's different about the active systems? Well, this is it. Here's these swimmers again, these little micro swimmers. Here they are swimming around all over the place. What do I need to put in my equations to understand what's going on there? Well, the answer is because they're swimming, they're creating flows in the fluid around them. As one of these little swimmers moves along, it's going to create flows. Just like if you're in the swimming pool and you're swimming, you get waves around you. And the shape of the flows is like this. These are experiments which measure the flow field a long way away from one of these tiny swimmers. And if you look at it, what you can see is it's pushing fluid out forwards and backwards and pulling it in from the sides. And this is pneumatic symmetry again, yeah? This thing's got pneumatic symmetry. This is a special axis, but this end and this end are the same. How do I put that into the equations? It's producing extra flows, which are going to give extra forces on all these little swimmers and extra stresses. The answer is that I put it into the equations like this, that I add one extra term down here, zeta, which is just a coefficient which says how much activity I've got, how many swimmers and whether they're swimming fast or not. And then a Q, which is this Q tensor, which says these flow fields have this pneumatic symmetry. And okay, I haven't told you why, but it makes sense. If I was just guessing on grounds of symmetry, this is what I'd do. Sriram Ramaswamy and colleagues did it better doing the maths properly. The important thing is that this term comes in there in the stress tensor. Okay, it's in the stress tensor, it comes under a derivative. So every time Q changes, if I have a change in the direction of this orientational order, if I have any kinks in my pneumatic order, you're going to get extra forces, extra stresses, extra flows. The punchline is this: any gradients in the order parameter gives you extra flows, induce flows in this system. So what? Well, let's look at our little localized distortion. This is a small defect. It's an unimportant defect, right? It would just relax back if I didn't have active particles. But now this is a place where the order parameter changes. It changes its direction. And so you're going to get forces and you're going to get flows. And if you work it out, that's the direction of them. And so what it's going to do is it's going to make that distortion worse. It's going to completely destroy that pneumatic order. Let's see if it's actually happening in an experiment. This is a lovely experiment done by colleagues in Barcelona. I mean, the problem is that you need to line things up first. You need to line them up in a pneumatic state before you can see the instability. And it's actually quite hard for these microtubules, which is the ones I'm going to show you. And the way they did it is basically by getting a graduate student with a straw who put it in the middle of a pool of this stuff and sucked, right? And then stopped sucking soon enough that it was all right. And so what that happens is that they pull the microtubules in and they line up pointing to the straw. So they've got them all lined up and then they stop sucking and you should see the instability. So let's look at it. I'll show it twice because it happens really quickly. Here we are. So everything lines up. And here's the instability. You can see the waves starting and growing. And then you can actually see a secondary instability where you get an instability in the perpendicular direction. Let me try and pull it again so you can actually see it. This is it lining up. They stop the alignment, and there's the instability starting. And then you can see it getting more and more convoluted, and what it ends up doing is this picture that I showed you before, and I will show you again now. You end up with these microtubules and motor proteins giving you active turbulence. But this is a nematic. It's a nematic, so we ought to have these topological defects. Here's the +1/2 defect. Okay, so now let's look for one. This one here is a +1/2 topological defect. This one here is a -1/2 one, and there's a beautiful one in the middle here with this threefold symmetry. This is turbulence with topological defects in. Let's solve the equations and look for the topological defects. This movie is our simulations, where I put a red dot where I have a +1/2 topological defect and a blue dot where I have a -1/2 topological defect. And what you see them do, is that they, I think around, yeah, this one is as a pointer. You can see them destroying each other in pairs. They come together in pairs, but then the number isn't decreasing. And if you look very carefully, let me play it again because I'm not very good with this pointer exactly how it works. What happens is that they also pop out in pairs. It's an active system, so you're allowed to pump, you're pumping in energy, and that gives you enough energy. So look up here in the top right-hand corner, and you'll see them pop out in pairs as well. This active turbulence is like a gas of topological defects. They're created in pairs, and they're destroyed in pairs. And what's more, these +1/2 defects are self-motile, because the order parameter is obviously changing. That means changing order parameter means extra forces and stresses, and these guys move on their own and in the background flow. These guys create flows, but because of the symmetry, they balance and they don't move. And so we now understand what is going on in these systems. I just want to show you what happens now if you take this active stuff and you confine it, mostly because they're nice movies. But also, you know, in real systems, you don't see turbulence so often. And maybe in bodies, the active material is confined. And if you do confine it, it doesn't do this turbulence. You get much more laminar flows. This one at the top shows you what happens in a channel. If we could only make more of this material, this is self-driven microfluidics. The trouble is that this microtubule motor mixture is great for experiments, but certainly at the moment we don't have a good enough material that's active to be able to do any sort of large-scale manufacturing. This one here, if I confine it in a circle, again, it goes round and round, it's self-propelled, it's active, and you see these things here, which are topological defects being formed. You occasionally get these defects, so you get a rather nice pattern, and this is macroscopic active matter, which is also good. Round. Okay, so that's the conclusion of this first part. It's gradients in this pneumatic order parameter which give you stresses and flows, and these destroy the pneumatic order to give you active turbulence. and active turbulence is characterized by these active topological defects. Let's think a little bit about epithelial cells. These are these squishy cells that I showed you, and they tend to form two-dimensional layers. Often in the body, they line the organs. For example, your skin is an epithelium. Why do I think these are active pneumatics? Well, how do they move? Let's look at ones which have been taken out of the body and just put on a Petri dish. So we're in a nice layer in 2 dimensions. Okay. These things tend to form 2-dimensional layers. One way they can move is like this. That's called flocking. They all move happily together in the same direction. Another way they can move, we've seen, this is this chaotic motion, which is active turbulence. Why do I think these cells are showing active turbulence, right? They're circular on average. I mean, they fluctuate a bit, but they're circular. And I've been going on about pneumatics. Pneumatics are long, thin things, right? Why is it okay to say that these show active turbulence? Well, this picture, I hope, explains that. What happens is that one starts with a cell which is round, and there's a bit of a fluctuation, and it becomes elongated. And then it pulls its neighbors. It's attached to its neighbors, so it will pull its neighbors in the same direction. And so you tend to get patches which are all extended in the same direction. These are results from an experiment showing the directions in which the cells are elongated. And you can see that there are patches which are pneumatically ordered, which are lined up with each other. And then here's a topological defect. Here's one of those +1/2 topological defects, and it's moving, which it's meant to do. So that works exactly like these active pneumatics. And then we tried an experiment where we counted the number of defects, and then we sent the cells to sleep by adding blebistatin, which is like a sleeping pill for cells. And the number of defects went down because the pluses and minuses joined with each other and annihilated, and there was no activity to make any more. And then around here, we washed out the blebistatin so that the things started making energy again, and the number of defects increased. I'm going to just show you my favorite experiment for a couple of slides. We'll get back to why these cells are active pneumatics in a minute. But this is an experiment from Milan, and I like it because it emphasizes how little we understand about biology. These are cells very like the ones I've just shown you. And in this first picture here, they're doing this active turbulence up. Doing the active turbulence, okay? And then the experimentalist added something called RAB5A, and no one's sure what it does, but they think it destroys the junctions between cells. And the cells immediately took off, started moving lots faster, and started flocking. Here's their speed as a function of time. Where's my pointer gone? There you go. Speed as a function of time. Okay, add the RAB5A, they suddenly take off. And then they slow down again. Somehow, mucking up with the cell-cell junctions in some way makes a difference. We don't understand that. We don't even understand something as simple as that. Here's a movie showing the same things. The one on the left, your left, my right, your left, I think, is the active turbulence. And the one on the right is what happens when you add RAB5A, and we're seeing the velocity here. And you can see they just take off like mad, just adding this chemical. I'd love to understand that. I don't understand that properly. Now, if I stop randomly pressing these buttons, we can see that movie once more, and then we'll move on to some research type things. Okay. I'm showing this because it'd be great if we have any biologists, experimentalists in the audience who want to have a go at it. Right, so now I'm going to talk about briefly about two different projects that we're interested in the moment, using these ideas of active pneumatics. The first is tumor distributions in late stage breast cancer. And this is work with Saraswat, who was my graduate student, now a postdoc in Dresden, and some amazing collaborators from Leipzig who actually know about the biology. And this is the problem. In the early stages of breast cancer, the system looks like this, where the cancerous cells are surrounded by a sort of fibrous layer of what's called extracellular matrix, loads of polymers around it, which basically act as a way to hold it together. And then the disease is not too bad, okay, because the cancerous cells are held in. After a year or so, this carcinoma in situ either explodes because of the increasing pressure of cells, or cells start to leak out. Nobody knows which, but what you end up with is a picture like this, which is invasive breast cancer, where the cells form these small purple clusters. These are malignant cells forming small purple clusters in a background, which I've got pink here, which is the extracellular matrix, basically collagen, long polymers surrounding the cells. And people, this is a histological slide. So slides like this of invasive breast cancer are taken routinely, obviously can't, yeah, which are taken routinely if you're unlucky enough to need an examination for breast cancer. And doctors can look at these and decide how bad the disease is. But they have no idea about why you get these patterns. And that's the question we wanted to ask. Why do you get these patterns? So the sensible thing would be to do an experiment. But these patterns move and evolve on timescales of years. And you can't tie down a poor person, or indeed a poor rat, for 2 years while you wait to see what's going on. So it is not possible to do experiments. Up to now, it has not been possible to do in vitro experiments outside the body, just because you can't set up a similar setup to see what's going on. However, there's lots of data of these images. We looked at 100,000 clusters from over 2,000 different patients, because these are stored in medical facilities all over the world. So we've got the data, but we'd like to understand the dynamics, and there's no way we can measure the dynamics. So how can we look at the dynamics of these sort of things? Well, let's have a look to start with and see what we might measure. So these plots are plots of the size of each of these clusters on the left-hand side, and the shape of each of these clusters on the right-hand side. They are log plots, and we want to look at the red curve at the moment. And what you see is there's a very nice power law, a very nice straight line here, which tells me how many clusters of different sizes. Here, there's a very nice line telling me how many clusters of different shapes. We measure the shape as the perimeter over the square root of area, so these pictures tell us what the shapes look like in the various points. Can we predict that in some way? I've explained we can't do experiments. So what can we do? Well, we know how to simulate this. We know how to model it. So what we want to do is model the dynamics. We think that we can model the cells themselves as an active pneumatic. So we use the equations I've shown you to model the cells. The surrounding extracellular matrix is like a viscoelastic material. So we use the equations of viscoelastic materials to model that. And then we'll see what we end up with. Okay, so this is the comparison between the histological slides at the top and the simulations at the bottom. Let's see what the simulations give us. Those are the simulations. The purple bits are the active matter. The purple bits are the cells, and the background is the extracellular matrix. What's happening in these simulations is that the clusters are evolving. They're stretching because of the activity. They're breaking up. You can see one breaking up down here with the black arrow. And then they're moving around and hitting each other and reforming again. You can see this happening with the red arrows. And so you end up with a steady state distribution. When I first saw this problem, I said, okay, so these things are changing their shape because they are growing, because the cells are dividing. We're now saying, no, they're ending up this shape because they're slowly moving around, hitting each other, coalescing, stretching, and splitting again. Does it look like the histological slides? Hang on, don't want that one. This one. Does it look like the histological slides? Yep. But of course, we had 2,000 slides to choose from. You don't believe me at this point. Let's look at the proper data. And on my graphs, the proper data is the blue curves from the simulations. And you can see that the match is actually amazingly good, given we don't really know the parameters. Here it's dead on, okay? Which is surprising. I don't believe it's that good, but I believe that the mechanism that we're using is likely correct. We estimated whether cell division and growth should be important. From the best numbers we can get, it's too slow to understand what's going on. So, yeah. So we change parameters. That's what you're meant to do, right? You just want to change the parameters. Does it change things much? It changes details, but it doesn't change anything else. So that's the conclusion. This evidence shows that cell motility is controlling this distinctive pattern of malignant breast cancer. And whereas medics are used to it, they use it every day. Now I hope we have a message about how they might understand it. Okay, and let me finish with one more story. And this is a story about the fact that actually I've told you that these cells are active pneumatics, but it's not quite that they're bog standard ordinary active pneumatics, because cells are deformable. Pneumatic molecules, pneumatic colloids don't deform much, whereas cells are squishy, right? They start round and then they're deformable. And that makes a difference. Before I forget, this work is done with Sumesh Tampi, who's just been made full professor at IIT Madras, who's wonderful, and a great graduate student, Marana Nejad, now at Harvard. Oh, and the other thing I mustn't forget is the disclaimer. We don't understand the biology going on here. I understand the physics, I can match the biology, but we really could do with a better understanding of the biology. So where this story starts is going back to this picture, okay? This was the flow field around a swimmer, and the forces are outwards along the long axis of the swimmer, and that's called an extensile swimmer. Some swimmers have the forces inwards along the long axis, and that's called a contractile swimmer. And everyone knows that extensile, some things are extensile and some things are contractile. And with swimmers, that's quite true. If you push like this, the shape doesn't change. But cells are squishy. Epithelial cells are squishy. If this is a cell, this blue thing, and I push like this, it's going to shrink. And it's going to grow in the opposite direction. And so it's changed from something which I would have called contractile to something which I would have called extensile. And indeed, it can be worse than that. If these cells are squishy, you could be pushing inwards like this. This could be the major stress direction, but the shape, the long axis of the shape, is along here. So there is no reason why the shape axis and the force axis are the same in these deformable pneumatics. The way to think of it in sort of biological language is that maybe you've got a layer of cells, and usually I would think that if, well, everyone assumes that if a cell's extended like this, it tends to pull itself back. So the contractile stress acts along the long axis. But then if you've got flows in this system, what can happen is the flows can come along and change the shape of the cells, but the stress fibers get left behind. And so the shape and the stress get decoupled from each other. Can we find any evidence, any experimental evidence for that? Well, here's one of these MDCK cells. And my colleague Jacob Nottbaum in Wisconsin and his students actually measured the shape axis of these cells and also the direction of maximum contractile stress. So the direction along which these cells are trying to contract. You do that by looking at particles in a substrate and see how much they're pulled. And here is a picture, which has gone wobbly on the slides, but it doesn't matter because we can see enough of it. What you find is that if the angle is small, I've put it in red. If the angle between the shape axis and the stress axis is small, these are the red bits. If the angle between the shape and the stress axis is large, these are the blue bits. And the red bits and the blue bits change as you move in time. You get really quite large angles between stress and shape, and they change with time. And luckily the slide's gone back to normal here because I can show you the movie of how these different regions change with time. I was a bit worried about these because, they're hard experiments measuring stress here. Can we do it with our equations? So there were the equations. This Q was the shape axis. Let's write down some more equations. So I've got one equation for the stress axis and one equation for the shape axis. I've decoupled shape and stress. The stress bit, that zeta q bit, okay, has to now be a stress bit. And then I assume that the things want to move towards each other. Solve the equations. The top is the experiments and the bottom is the simulations. First time, never usually works like that. Really, this physics is very robust. So now we understand the physics, okay? But what we don't understand yet is exactly what's going on with the biology. So here are my conclusions of this part. And I am going to play one more movie because this is what we're aiming towards. This is Drosophila embryo, which is growing into a fully grown Drosophila over the scale of 1 day. This is an active system. You have forces, you have flows, and you have pattern formation. And putting together the chemistry and the mechanics, hopefully one day soon we're going to be understand exactly what's going on here. Thank you very much for listening.
Thank you for showing us the principle of active matter. Reveals a beautiful and energy-driven choreography coming to cell and birth. So your insight offers a fundamental, profound new way for understanding pattern formation from development to disease. Before I open up for the questions, may I ask you the first question as someone working on energy field? In your beginning of your talk, you mentioned energy is a fundamental currency that powers everything from molecular motors to collective flows. In engineering, in particular, in my field, people think about energy efficiency and optimizations. In biological systems, do we have any evidence of energy budgeting or trade-off?
Good question. That's what people are trying to think about. What people are trying to think about quite a lot now. These molecular motors are meant to be about 80% efficient, so more efficient, I think, than macroscopic engines, which is one of the reasons it would be nice to build something. But no one's quite sure about the exact energy budget of a cell, and it's definitely a topic of research. It's a very important question.
It's super to know the efficiency up to 80%. In my field, the power plant, modern power plant efficiency now just around 40 or 42%. So we need to learn from our nature, right? Now I open up, floor for questions. Yes.
All right. Thank you very much. Thank you for a very informative and inspiring talk. I have one little question. In your show of the breast cancer cell, and you said that it's really the motility rather than the biology. So maybe we physicists can do something. Have you thought about adding in the equations some force that could put these spread out cancer cells coalesce together, or at least bundle them together so that they wouldn't just keep on spreading to the whole body?
Yeah, you can certainly do it in the equations, but translating the equations into the amazing things doctors do is not possible, I think. I think the thing we can probably do, which might be useful, is look at this earlier stage where the rather larger cluster breaks up and ask, how might it break up? Because people are starting to be able to do experiments at that early stage and just starting to see how clusters of cells in pretend extracellular matrix are managing to break up. So then we might have a better understanding, which might be useful a long way downstream.
Right. For example, you mentioned earlier that the boundaries would change the way that they flow, and presumably there's some motility inside the boundary, right?
Yeah.
Is there some way to reinforce it or do something to contain it before it gets bad?
I think you would need to do it at an earlier stage. And I think the body does it. It's doing it with this extracellular matrix. It grows around the big tumor before it breaks up. But then one is stuck later on. But yes, that's the sort of questions that one needs to ask. But I always feel a bit guilty that this is really fundamental science, and the doctors are doing a great job of actually doing, perhaps rather than understanding.
Well, it's already a great contribution. That you can see that physics actually plays a role. Yeah. Thank you.
Yes, Professor Xu.
Work. So I'm a fluid person. I want to ask two questions about the turbulence. Number one is there any factor that determine your chirality? How do you determine in which way it rotates? Is it the initial angular momentum or any?
It's random. It's a symmetry breaking thing. Yes.
Okay.
So
okay.
equally, as long as the particles, the active particles, are not chiral.
Oh,
it's
okay.
just random.
So the probability is the same.
Yeah.
Okay.
Yeah.
The second one is, do you have any parameter like for the fluid turbulence Reynolds number, right? It can determine when it will occur, but for this one, the Reynolds number is very small, as you mentioned. So, do you have any parameter that can tell us roughly when it can happen?
Yes, in these active pneumatics, they're unconditionally unstable. So it will always happen if you turn on any sort of activity, even at 0 Reynolds number. But then if you want to, the confinement does give you a scale, and it's the turbulence tends to have lots of vortices, and it's if those vortices can't form because it's confined too much, then it will start getting laminar flows rather than turbulent flows. And that length scale depends on how easy it is to distort the active pneumatic and the strength of the activity.
Oh, so it's mainly determined by a length scale.
It's determined by a length scale in terms of confinement, but actually whether you get turbulence, you always do in these systems.
Ah, okay.
Yeah.
Thank you.
Yeah.
Yeah. Yes. Thank you again for a very exciting presentation. I'm a mechanicist by training and a biomechanicist, actually. My first question, I have two questions. My first question is more about the mechanics. Do you uncouple the stress from the shape or deformation towards the end of it? What kind of constitution relationship did you assume in doing that? This one thing. It's my first question. Second question is about more other issues. Yes.
Okay. We essentially don't. The structure of this thing is not viscoelastic. The structure of the fluid is just really input because we have an equation for the Q tensor, which is a bit like the conformation tensor in a dilute polymer suspension. So the only extra thing we would have is if you stretch the polymers, they will relax back to equilibrium. So it's that sort of thing. So we don't have a fancy constitutive relation.
All right. Okay. I'll look into that more. Okay. My second question is very, very different. In the beginning of your lecture, you draw an analogy of a crowd movement of people to a kind of active matter. I would look at a person as a active, of course, active, but also with a volition. Okay, have an intention to go. Okay, sometimes against the crowd, for example. How would that type of thing can be modeled in active systems like that?
That you could model by having a particle. I mean, you can have particle-based models, although I didn't talk about them. You could have a particle-based model which didn't obey the rules. But that's why we look at these tiny things, right? They're a bit easier. They don't suddenly do something wrong. The sort of large animal active matter is very interesting, but like you say, it's not just the activity, it's what they decide to do as well.
Other questions? Give you more time to think about your question. I ask 2 questions from online side. First question, what's the role of active matter in optimization and survival of a fittest?
Oh, good heavens. I don't know the answer to that. Active matter is biology, so biology would be survival of the fittest. So that would be really aiming at evolution. Someone's thinking about evolution. I don't think those are really related questions. I think, yeah.
Second question, how can concept from active matter be applied to understand fourth generation in living cells? Fourth generation.
Fourth generation. Okay, well, I think what I was talking about with the motor proteins at the beginning is sort of the answer to that. Those are the forces that move things around in living cells. They are powered by ATP, which is sort of energy from their surroundings. They take in the ATP, and then this protein is specially organized, these little motor proteins. So the way it works is that the back foot binds to a molecule of ATP. That releases the back foot. Because of the shape of the protein, it moves forward and it tends to attach. It tends to attach further on onto the microtubule in front of it. That changes the binding at the back foot and it gets ready to attach another molecule of ATP. So that is understood how these things move along, and they're the basic engines of the cell. Yeah.
Thank you. Any more questions? Yes.
Thank you, Professor, for a really interesting talk. I'm a postdoc from PolyU, and I also did a little bit on the biophysics, so I'm quite interested in this topic about active matters. So when we're modeling this kind of particles or cells, can we also include their life cycles, for example, reproduction or the death of the cells inside?
Yes, but it depends which question, what sort of modeling you want. We can certainly include cell division in here. Actually, cell division is a bit like extensile activity, because if a cell divides, it pushes outwards like this.
Yeah, and there's another follow-up with this. For example, if we include more things, will this influence their patterns or the topological defects in this kind of turbulence?
It depends which things you include. Certainly, cell division acts like activity.
Yeah.
So I would expect it to enhance active turbulence. But then there's all sorts of things going on inside a cell when you have cell division, you know, the formation of the spindle and things like that. You'd have to sort of start again then and model it on a smaller length scale. People have tried to do that. Again, the spindle is an amatic-like object.
Yeah, thank you.
Yeah.
More questions? Yes.
Hello, beautiful talk, Julia. So the last part of the talk about shape just misalignment is very interesting and intriguing. So in the past, people have associated topological defect in cell layer to their functions, like extruding dead cells or non-functional cells from the layer. So this would change. So what kind of change would this new concept or conceptual idea bring to these ideas?
I don't think it's particularly relevant to that one. but I think it's relevant to how these cells move. People don't really understand what the forces are acting on the cells. For example, you've got the focal adhesions pulling on the surface, which is probably a polar force, and then you've got them pulling on each other, the cells, through probably stress fibers. And it's, I don't know, I mean, people really just don't know how the cells interact properly with each other. I'm sure you've heard of contact inhibition of locomotion. Yeah, when they, you know, this is a rumor, really. Nobody's really proved it. And so it's just another way, I think, of maybe something we have to think about if we understand what's going on in these cell layers.
Yeah, it would be interesting to explore the consequence.
Yeah, absolutely, absolutely. So it's the consequences. At the moment, we understand the physics. We do not understand the biology at all. And I am at the moment concerned, this is probably, you're not allowed to say this, but I worry about traction force microscopy. We have now done a simulation where we have an active layer and an underlying passive layer. And you'd think that the passive layer would reflect what was happening in the active layer, coupled through friction. And it doesn't. It acts as a low-pass filter, and you get a different pattern on the bottom layer. So at the moment, we're exploring whether if we use traction force microscopy on our simple simulations, it will give the right answer.
Wow.
So yeah, loads of things I don't understand there.
Okay, thank you.
Well, Professor Xu's, question, what's the main difference between low Reynolds number turbulence and high Reynolds number turbulence?
Yeah, it's I got really told off for calling it turbulence at low Reynolds number, because to the experts, turbulence means high Reynolds number. But high Reynolds number, one has Kolmogorov scaling. The energy is pumped in at large length scales and then cascades down to small length scales. We do not have any similar scaling here. Energy is pumped in on the scale of the individual motors and probably dissipated on the scale of the little vortices, but no obvious scaling. So I think they should be seen as really rather different at the moment anyway. And perhaps I shouldn't call it turbulence. I mean turbulence in the general sense of chaos. But what is the same, which is fun, is that active turbulence and elastic turbulence in dilute polymer suspensions, we now think is the same. Yeah.
Any more questions, comments, or suggestions from the floor? Yes.
Oh, I know, it's wonderful, isn't it? Yes, it's great. I want to take it home. I mean, I think these they might be bubbles. They could be bubbles, but I think they're probably vertex models of cells, and which some clever person has made into this pretty picture. Yeah, it's great.
Super. Before I pass to Professor Ching, the Peierls director, may I propose a big hand to our speaker. Professor Ching.
Well, thank you again for Professor YEOMANS for your wonderful talk. It's really very inspiring. And also for Professor Wang's being the moderator, you have done a very good job. Thank you very much. So to express our appreciation to the distinguished speaker, we prepare a souvenir for you. Please come to the front. This is a plaque with your lecture title and your name on that. And yes, let's take a photo together. One also on some kind.
You the opportunity come. This way.
All right, thank you very much. Peer organized distinguished lectures and seminars from time to time. We often announce this through the internet. I would like to ask your attention to our next lecture that will be on the 7th of January. Will be given by Professor Wang Zhonglim from the Chinese Academy of Science. So Professor Wang is being listed at the #1 in the top 2 scientists given by Stanford University. I don't know the total citation. I think it's over 500,000, something like that. Okay, so I'd like to thank all of you for attending the lecture today, and especially for those who asked questions to make this lecture very beautiful. So this lecture is adjourned. Thank you.